Hey guys, this is the notes for Chapter 12, Section 2, Chemical Calculations. It's the first part of this section, and we're going to be talking about this thing called stoichiometry, which is a really fun word to say, so I highly recommend you actually say it out loud. Stoichiometry. It does very fun things. Okay, so what the heck is stoichiometry besides being something that's really fun to say? So stoichiometry is talking about the relative quantities of moles and their calculations that make use of mole ratios. What the heck is a mole ratio? So stoichiometry is just basically doing a bunch of calculations to figure out how much stuff do you need to work with this much stuff to make this much stuff or whatever. And we use the balanced chemical equation. Let me show you that now. So think about this reaction. So you've got ammonia reacting with oxygen. So here's ammonia reacting with oxygen, and that produces water and nitric oxide. So the way it says in this is for every 4 moles of ammonia, and the 4 comes from that coefficient in the balanced chemical equation. So we have every 4 moles of ammonia react with 5 moles of oxygen. See how the 5 is actually talking about the number of moles, which is a chemical quantity. And that will always make, when you have 4 ammonia and 5 oxygen, 6 moles of water and 4 moles of nitric oxide. NO is nitric oxide. So with this equation, we're able to come up with mole-mole ratios. So how many moles to how many moles. So you can relate different things together. So you know that for every 4 moles of ammonia, you need 5 moles of oxygen, 6 moles of water, and 4 moles of nitric oxide. So before, when we did balanced chemical equations, we were talking about just a molecule, just atoms, and now we're going to just make it bigger so it's a tangible amount, something that humans can actually see. A mole is a lot bigger than an atom, way bigger, and we'll get into how much bigger in the section about what moles are, but for now, just think of it as a unit. So 4 units or moles of ammonia, 5 units or moles of oxygen, 6 units or moles of water for every 4 units or moles of nitric oxide. Those numbers came from the coefficient in your balanced chemical equation. And you're going to use these to make fractions for conversions, and they're called unit fractions because all of these end up kind of being equal to one another in a way. So for every 4 moles of ammonia, you have to have 5 moles of oxygen. If you use up 5 moles of oxygen, you will make 6 moles of water. If you produce 6 moles of water, you'll also make 4 moles of nitric oxide. So let me show you what I mean by those fractions. So let's come up with a few. 4 moles of of ammonia for every, well, how about 5 moles of oxygen? So if you have 4 moles of this, you need 5 moles of that. That could be equal to, what else? 4 moles of ammonia for every, well, we've got 6 moles of water. You could also do 4 moles of ammonia for every 4 moles of nitric oxide. So these are all unit conversions. It's stuff you're getting from the balanced chemical equation, and you're setting it up how much of different things you need for every 4 moles of ammonia. So I just set them up for ammonia. The other way to think about it is with your oxygen. So for every 5 moles of oxygen, what do you need? Well, you need 4 moles of ammonia. Or you can think of it as if you use up 5 moles of oxygen, what would you make? Well, one of the things you'd make is 6 moles of water. 5 moles of oxygen would also make, go over here, 4 moles of nitric oxide. All right, now we're going to do it for water. If you made 6 moles of water, how much ammonia did you use? Did you get 4 moles of ammonia? Good. And then for every 6 moles of water, how much oxygen do you need? 5 moles of oxygen. And the last one for water on the top, for every 6 moles of water, you would also produce 4 moles of nitric oxide. So then the last 3, I'd like you to pause the video and come up with the last 3 unit conversions using nitric oxide on the top. All right, so we're going to go over those answers. Did you get 4 moles of nitric oxide on top for every 4 moles of ammonia on the bottom? So this is relating nitric oxide to ammonia. 4 moles of nitric oxide for every, did you get 5 moles of oxygen on the bottom? 4 moles of nitric oxide for every 6 moles of water. So all of these are part of the same balanced chemical equation. So there's different points. Notice over here, for example, we're relating ammonia to oxygen, where ammonia is on top and oxygen's on the bottom. You can find another fraction that has ammonia and oxygen. Look right below it. This is where I have it written. Notice this is the same but opposite. You're going to have to pick which unit conversion you want for each balanced chemical equation. All of these are called unit conversions, and the reason is they're technically equal to 1. How are they equal to 1 if they have different things in the top and the bottom? Well, 4 moles of ammonia for every 5 moles of oxygen, it's just talking about different parts of the same balanced chemical equation. So you're not talking about a different equation. You're talking about one round of this equation. So technically, if you have 4 moles of ammonia, you need 5 moles of oxygen. So they're talking about the same reaction, so those are going to be equal. We're going to come back to this, and we're going to be using these for the rest of the school year, so you'll really get used to how to come up with these unit conversions and when to use them. All right, so when you're working through these problems, you're always going to use the following setup. Always take whatever is known in the problem, so you're going to be given something like, oh, you've got 10 grams of water, or you've got 24 moles of nitric acid, or whatever is given to you. Like, what do you actually have? Then you're going to multiply that, so you're going to do an x, and we call it x line. So do an x and then draw a line straight out from it. Multiply it by a unit converter, or maybe more. If it's going to take multiple steps to convert, you might need multiple things for an x line. And then you multiply things and get your unknown. Choose the unit converter that will cancel out the units of your known and get you closer to your unknown. It might get you right to the unknown unit in one step, or it might be a multi-step problem. Once you have your x line drawn out, everything on the top gets multiplied, and you divide by everything on the bottom. Remember, if the number is 1, you can ignore ones, but any other number you have to keep track of. So here's how it's going to look. You're going to take your known, and you're going to multiply it by some fraction. So that's why you draw an x, and then a line straight through, so an x line. Whatever unit you want on the bottom, so you're picking from that list that we made before with your balanced chemical equation, it has to cancel units with your known. So if your known is moles of water, then you're going to need moles of water on the bottom, because if you multiply by everything on the top and divide by the bottom, when you divide by the same thing, things cancel out. On top is going to go to your new unit. Now, if it's a one-step problem, it'll be the unit that you want, but it might in other problems just get you closer to being able to convert to the unit you want. Notice that each part of this is going to be equivalent to one another. And when I say equivalent to one another, I mean like they're coming from the same balanced chemical equation. So you have that mole to mole ratio. So like we listed all of those fractions before, how many moles of ammonia for how many moles of oxygen, etc. It has to be equivalent to one another. And that's going to get you your unknown, or the answer to your problem. So let's do some practice ones. All right, so we're still working with the same balanced chemical equation as before. So what I'm asking here is how many moles of oxygen are needed if 8 moles of ammonia react. So this is one that you can kind of do in your head, and I wanted to start with a really easy one so that I can show you the steps, and then you apply the same steps now that it makes sense. So let's look at this. For every 4 moles of ammonia, you need 5 moles of oxygen. Well, if you have 8 moles of ammonia, then this reaction is going to happen 2 times. So instead of 4, I used 8. So instead of 5, I would need doubled. So it would be 10. But let me show you how to set it up so that you know the basics of setting up a problem, so when we get to a more complicated one, it makes sense. So you always list your known first. In the problem, it says how many moles of oxygen, so that's your unknown, I don't know, it's got the question, are needed if 8 moles of ammonia react. So you know I've got 8 moles of ammonia, NH3. So that's what you list first, 8 moles of ammonia. Once you list your known, you draw your X line. So here, you need your unit conversion. So I want you to look at all those unit converters that we listed, all of them from our balanced chemical equation. We need one that's going to get rid of moles of ammonia on the bottom and go to moles of oxygen on the top. You want to get rid of this. So 4 moles of ammonia. That comes right from your chemical equation right here. Well, for every 4 moles of ammonia, and I need that on the bottom so that these will cancel, I have 5 moles of oxygen, so that goes on the top. Moles of ammonia and moles of ammonia cancel, because if you have something on the top and the bottom, you're able to cross them out. All right, so we multiply 8 and 5, because those are technically on the top, and you divide by 4. 8 is on the top because this is, whenever you don't see a fraction, it's technically a fraction over 1, but we don't care about ones. So 8 times 5 divided by 4, our only unit left is moles of O2, so that's what our answer is in. So we know 8 times 5 divided by 4 is going to get us 10 moles of oxygen, which is what we said at the beginning. All right, if you have any questions here, make sure you stop and ask a teacher before moving on. Let's go to the next problem and make it a little bit harder. Oh, I forgot one note. Remember, you need that properly balanced chemical equation or you wouldn't have gotten the right answer. So if you didn't know that the coefficient here was 4 and the coefficient here was 5, you wouldn't have been able to get this and you wouldn't be able to answer. So always check to make sure a chemical equation is balanced before doing all these calculations. All right, next one. How many moles of water are produced if 0.176 moles of oxygen are used? Keep in mind we're talking about moles, we're not talking about molecules, and a mole is a large quantity of particles, so you can have a fraction of a mole. You don't need whole numbers. All right, so in this question we're asking how many moles of H2O, that's your unknown, I don't know, are produced if 0.176 moles of oxygen, there's your known. That's what you have in the lab. That's what's being used. So you're going to start with your known, draw your X line. The unit that goes on the bottom, so always start on the bottom based on canceling. The unit that goes on the bottom is the one that's going to cancel. So we need moles of O2 on the bottom. We're going to pull, if it's a mole ratio, you're going to pull moles from up here. So moles of O2, here's O2. We know we have 5 moles of O2. So that goes down here, 5 moles of O2. The 5 is the coefficient that matches oxygen. We want moles of water. Can we relate oxygen and water? We definitely can, because we have 6 moles of water up here. So that goes on the top. All right, multiply on the top, divide by anything on the bottom, cancel units that are on the top and the bottom. Moles of O2 go away. We're left with just moles of water, and that's what we want as our answer. So when you do 0.176 times 6 divided by 5, you get 0.211 moles of H2O. Go ahead and do that in your calculator to make sure you get the right answer before moving on. For this last problem, how many moles of nitric oxide are produced in the reaction if 17 moles of water are also produced? So go ahead and use the same skills we had. Think about what you're relating, nitric oxide, NO, to water, H2O here. Write down what you think it is, freeze your computer, and when you're done, turn it back on and see if you got it right. All right, so in this problem, 17 moles of water are our known, so that's where you start. The goal is to get to moles of NO, so we need a unit converter that relates water and nitric oxide. Which one of those is going to be drawn on the bottom of our X line? Well, it's the one we need to cancel. So if you look at the problem, what do we need to cancel? Well, we need to cancel the moles of water. So moles of water need to be put on the bottom of the next one. How many moles of water? Well, look to your balanced chemical equation. It's 6. So 6 moles of water. We want moles of nitric oxide. So look at the top, look at your chemical equation here, boom. 4 moles of nitric oxide. You're going to cancel out moles of water because you have it on the top and the bottom. You're left with what you want, so you know that works out. You have 17 times 4, because those are both on the top, and divided by 6 on the bottom. 11 moles of nitric oxide. Okay, best of luck answering questions. Make sure you talk to your teacher if you have any before moving on. Good luck!